Thanks. Thank you, Alex, for the introduction. Yeah, this is a joint work with Jonathan, who is also here in the audience. And yeah, I'm going to talk about autumn scoring for dynamic information acquisition. So consider the application where there is an expert who can acquire information for predicting a future event. This can happen for a lot of applications. For example, you can think of a financial advisor who can acquire information about the markets to predict the future market outcomes. Or you can think of a political advisor who can acquire information to predict the election outcome. Or you can think of the most classical application of forecasting, which is a weather forecast. Try to acquire information to predict the future weather or about the natural disasters. And the important feature in our paper is that we are considering a dynamic environment in the sense that the expert can repeatedly acquire information over time until a deadline reaches. This deadline can be, for example, a deadline where a decision maker needs to make decisions that gets him some payoff depending on the future event. And naturally, this deadline, naturally the future state will only be publicly revealed after this deadline, where the expert can acquire information. Of course, in those models where the experts can acquire information, those information are costly and usually do not directly benefit the experts. So for a principal who wants to get this precise information from the experts, she can just design contracts for incentivizing the agents to first acquire costly information and then truthfully report it back to the principal. One example you can think of is that an investor wants to invest in the financial markets, and she can design contract to interact with a financial advisor so that he can acquire accurate but costly information regarding the future markets. And the goal of our paper is try to think about how to design the optimal dynamic contract in order to incentivize the expert to acquire costly information. And we are going to do so subject to a budget constraint of the principal. So this is the main goal of our paper. And next, I'm going to tell you a little bit in more detail of the exact model of our paper. In our paper, the unknown future event is modeled as a binary state. Of course, this is a restricted assumption, but it captures many applications I talk about. For example, the binary state can represent whether the market price will go down or go up in the future, or whether a candidate will be elected or not. And the time is discrete, and the unknown state is the initial unknown to both the principal and the agent, and it will be eventually revealed to the public after the time horizon capital T. In this dynamic model, I'm next going to give you about the details of the expert's information acquisition process. At any point in time in this dynamic process, the agent can choose to make a binary effort decision for acquiring information or not. If this agent at any particular time t chooses to exit the effort for acquiring information, then he can find some evidence or some signals with some probability lambda times delta. For the simplicity of this talk, we are going to just focus on binary signals. Signal good and signal bad, where the good signal indicates it's more likely that the underlying state is 1, and the other signal indicates that when the expert sees it, it's more likely that underlying state is 0. Of course, the expert can also choose to not exit efforts. And in that case, he does not need to pay any cost, and no information would arrive. An important part that we need to notice for this particular problem is that if the agent chooses to exit effort, even if he doesn't see any signal or any evidence, this is a still informative event, and the agent's belief may still update after not receiving a signal. And without loss, we just assume that if the agent doesn't see the signal, his belief just drifts towards believing state zero is going to be more likely. One assumption that we are going to assume carry out our paper is the single evidence assumption, which means that there exists at most a single piece of evidence. Note that in our model, the evidence are not conclusive. So even when the agents observe an evidence, he is still not fully informative about the underlying state. But our assumption assumes that nevertheless, the learning will end after that. In this information acquisition process, both the cost of the agents and the arrival rates of the evidence when he chooses to exit the effort are both public information. So the principal can observe those numbers. However, both the effort choices and the arrival signals are private information of the agents. And since this is a contract design session, one important difference between our model to the classical contract design is that the arrival signals are private information of the agents. This means that not only we have more hazard because the effort choice is not observed, we also have endogenous private information in the sense that the agent would hold private information about the underlying state based on his effort choices. In this dynamic problem, the principal can design dynamic contract for rewarding the agents and get precise, accurate information. And the contract works as follows. At any time t, the agent can choose to send a message to the principal, and we use h of t to denote the full history of the report that the agent has reported to the principal. And the contract is simply a mapping from the full history of the report and the underlying state, which can be verified in ex post, to a reward of the agent. Note that we have both the limit liability constraint and a budget constraint, which we normalize to equal to 1. And the agent's utility is simply his reward he can collect from the contract minus his cost of effort in the information acquisition process. And the agent's goal is simply try to find the best effort choices to maximize his own utility. One strategy the agent can adopt for maximizing his utility, giving any arbitrary dynamic contract, is just using a stopping strategy, meaning that for the agent, there always exists a stopping time tau before the time horizon capital T, such that the utility maximizing choice is just to always exiting effort before time tau if he hasn't find any signal, and he will stop immediately. Either he receives a signal or the stopping time is hit. Okay. And the goal of the principle is to design a dynamic contract, of course, has to satisfy the budget constraint to maximize the stopping time of the agent. So the justification of this objective is that with the larger stopping time, this means that the agent is getting more precise information, and this always benefits for the principal. Our paper is related to many lines of work. The most relevant line is about incentivizing information acquisition using static contract or using scoring rules. I'm going to tell you a little bit in more detail about our differences to that line of work in the next few slides. Okay. For this talk, I'm going to do a relatively unconventional choice, which I'm going to tell you about my results only at the end. And for the most part of the talk, I'm going to give you an intuition about why dynamic actually matters in our model and why it is interesting to look at dynamic information acquisition problem. So even though the agent is acquiring information in a dynamic process, one very naive choice that principal can actually do is to say, I'm going to ignore how you acquire information in this dynamic process. I'm going to just adopt scoring rules at the end of time horizon for eliciting your posterior beliefs based on your aggregate information. And this actually has been done in the past work, for example, in the paper by Neyman, Norov, and Weinberg. Yes.
It's not like the state will realize in the very end.
Yes, the state will be eventually realized, and the principal can observe that.
Realize according to the posterior.
There is a prior. There is a prior belief about the state, and the state is going to realize according to that, and the agent is going to get signals based on the realized state. So one big question here that we try to address in our paper is that is this very straightforward approach without loss of generality? And a very simple answer by our paper is that it depends. And later I'm going to give you conditions when it holds and conditions when it doesn't. But first, let me just try to tell you why this might not be without loss. And I'm going to give you the intuition by giving you a revisit of what the optimal scoring look like in the static model. So in the static model, there is still a binary state drawn according from some distribution. The only difference is that the agent doesn't need to acquire information dynamically. He just needs to make a one-shot decision of exiting effort for acquiring information or not. And the principal still want to design contract for rewarding the agent for acquiring information. And the objective is still trying to incentivize the agent to exit effort, subject to a budget constraint on the contracts. For this static problem, we actually exactly know how to solve it. And the optimal scoring rule in the static model would look like follows. So this is what we call a V-shaped scoring rule. The exact description here for the scoring rule might look complicated, but it has a very simple and intuitive indirect implementation in the sense that the optimal scoring rule can be implemented by simply asking the expert to predict what the underlying state is. If the expert predicts the underlying state is 1 and the prediction is actually correct, the expert gets 1. And if the expert predicts the underlying state is 0 and that's correct, the reward would be R0, otherwise the reward is 0. So the expected reward of the experts would have this V shape, and this is why we named the score rule. And in a previous paper with Jason, Li and Yifan, we actually show that this V-shaped scoring rule is optimal in the static model, and in particular, the kink of the V-shaped scoring rule located exactly as a prime. The main reason is that this particular V-shaped scoring rule make it indifferent for the agents to make the prediction on whether state is 1 or state is 0. This means that information has most value to the agent, and hence the agent has most incentive to acquire additional information. Next, I'm going to tell you, suppose we just took this solution from the static model, why it would fail in the dynamic environment. The main reason is that in the dynamic process, when the agent choose to exit effort for acquiring information, even if he doesn't receive any signal, his belief may still drift over time. And for example, when the belief of the agents after several periods until time t drifts towards 0, this means the agent is more and more certain that the underlying state is going to be 0. And he is more and more certain that betting that the state is 0 is going to be the optimal report. This means that his value for getting additional information is going to be very small because he knows what the optimal report is the principal, and hence the agent may just stop early for exiting efforts. And this may be bad for the principal. The illustration is for V-shaped scoring rules, but it holds more general. If you just use a single scoring rule, it may not provide the optimal incentive. Instead, what we can show is that the optimal dynamic contract can have the following feature, meaning that it can have a weekly decreasing reward to the expert over time for reporting his belief. In particular, the principal want to decrease the reward in the state that the agent becomes increasingly certain of. This would gradually decrease the agent's utility if he just chooses to shirk and not exceeding effort. But aside, so a very tricky part in here is that, note that I only said weekly decreasing here. This is because if you try to decrease the agent's reward at time t, of course, it provides stronger incentive for agents to exert effort at time t. But from the perspective of an earlier time periods, this actually creates a weaker incentive because the continuation value for the agent for acquiring information is going to be lower. So in the optimal dynamic contract, we need to carefully balance these two incentives. And essentially, our result, we are going to show that to achieve the optimal balance, in some cases, static scoring is going to be optimal. And finally, this is the formal result I promised you earlier. We show that the optimal dynamic contract can be implemented in a static manner or can be implemented as a scoring rule in any of the three canonical environments. The first environment is the station environment, where essentially not receiving a signal is not going to be informative. This is an environment that the tension of belief drift goes away. The second environment is what we call the perfect learning environment. This is the environment is that whenever the agents receive a signal, it's going to be perfectly informative about the underlying states. And finally, we have the single signal environments. You can view this environment as if the agent doesn't receive any signal, it's going to be very informative and his belief is going to be quickly jumped there. And we also have a partial converse by showing that if all three conditions are sufficiently violated, no optimal contract can be implemented as a static contract. I'm not going to tell you about detail of how to prove this, but one additional thing I would like to say is that even in the environment where we can show that a static contract is optimal, the optimal static contract does not need to coincide with the static model. In particular, the V-shaped scoring rule with a kink as prior may not be optimal. We can show this in the example of the perfect learning environments. Due to the limit of time, I cannot give you further details on the intuitions. And we can also show that in the environments with single signal in the single signal, the optimal scoring may not even be V-shaped. Okay. And if you are interested in the full characterization, welcome to read our paper or ask me after the session. Thank you.